Ooh, you're nice. Mm. One, two, I think in the Chrome bill like this. Shalom. They're going to wait now until okay. Go and check out this video. Hmm. Solomon, I beg you come set up this thing for me. Mm. Okay. Hello. Okay. The the class is going to start soon. Please, once I see 10 hands, I'll start the class. So you all should get in, so we'll get to it. Hello. Okay. The the class is going to start soon. So once I see 10 hands, I'll start the class. So Um, okay, so I don't think we'll keep waiting. Let's just get into the class for want of time. Yes, let's start. Okay. Um, so that you guys can be able to go and do your own personal study. Before we continue, first of all, I would like to introduce. My name is Godson, and this is basically a class to help you understand some of the things in BCH. Some we're not going to discuss everything, obviously, but we'll try to make as many as we can understandable. Now, it is important that if you come in, you like the video. You get, so please, as you're coming in and you're waving, just click the like button to like the video. If you haven't subscribed to my channel too, it's also important that you do so. You get, it's free. You don't pay to subscribe. Okay, now with all those things said, let me just bring up my board. Sorry, I hadn't set that up earlier. Let me bring it up. Yeah, okay, just give me 1 second. Nah, not 1 second exactly, but a little while. Okay, my board is set. Is it set? Is it set? Let's add the Windows capture device. Where is it? Okay. Okay, I think, yeah, my board is set. Let's confirm. Uh, okay, sorry guys. Let me just quickly set up my board. It's acting up. Okay, so while that is happening, I would just like to say or remind us that basically most of us were in yesterday's class. And in yesterday's class, we talked about some introductory parts of organic chemistry. I, for one, asked you guys to review some studies, and those studies are going to help us out in no small way. Now, having said that, we would actually start today's study by looking at important reactions of your aldehydes, and then we are going to do a little bit of one or two things on naming. You get, I'll just say one or two things on naming, and that'll be that basically. You get, then we get into your carbohydrates, and after discussing the carbohydrates, we get into the lipids and see how far we can cover as much as possible, because this is supposed to be a 2-hour class so that you guys can have time to go back and do your personal studies. Okay, I think my board is set. Let me confirm. If you can hear me and you can see the board, it's important. Just indicate. If you can hear, just say I can hear so that I'll be sure. Bio 151 revision. Okay, if you can hear, just quickly indicate. Just type it. Sir, shey laptop no dey up today. Okay, I hope so too. You get, so please indicate if you can hear me so that I'll know what I'm doing. You get, if you can hear me, indicate. Basically, I don't have a monitor sound here. Okay, very good. Whichever Mary you can hear me. So let's just move ahead. Now, having said that, today's class we are going to continue from where we stopped yesterday. And basically we are discussing the aldehydes before we left off study. You get, and in discussing the aldehydes, one of the most important things we said in yesterday's class is an aldehyde is characterized by the presence of C double bond O. Now, an aldehyde is also known as alka. Now, this particular aldehyde has C double bond O terminally, which means that anytime you see C double bond O and it is terminally positioned, it is an aldehyde. But if it is non-terminally positioned, it is a ketone. And it is important to understand this thing because we are going to delve into carbohydrates. So for those of you that did not review or you are not with us in the last class, today's class might be a little bit confusing. You don't need to bother so much. I'm just going to touch one or two things. This is one of the things I'm going to touch. The aldehydes are characterized by terminal C double bond O, which means that if you have a chain of carbon atom and you notice carbon double bond O, this one now, because this is the last carbon atom and this last carbon atom has the double bond to oxygen, this one is an alkyl or aldehyde. But in the case where you have this, where the C double bond O occurs non-terminally. When you say terminal, it means the last carbon, either from this end or from this end. Non-terminal means the one that is in between. So if I write this, this is also a ketone. Sorry, why is it a ketone? Because this C double bond O is not occurring terminally, it's occurring non-terminally. Okay, so That's that majorly. And it's important to understand this because we're going to be using the aldehyde and ketones through carbohydrates before we drop it and then get into lipids. Even in lipids, self, when we come across our galactolipids, we are going to find out that we need to understand this thing I'm saying now. So please, emphasis, aldehydes and ketones. Aldehydes and ketones are both characterized by the presence of C double bond O. But in the case of aldehyde, this C double bond O is terminal. Terminal. That is, it occurs on the last carbon. Okay, let's look at this structure for instance. Imagine I have this. Imagine I have this. And I have this. Sorry, let me remove. And I have this. Same benzene ring. Okay, so amongst the two of them, this is A and this is B. Just to clarify again, can you please indicate which one is an aldehyde and which one is a ketone? Once I have one answer, I will move ahead because we discussed this yesterday. Which one is an aldehyde and which of them is a ketone? Okay, so just indicate quickly which of these is an aldehyde, which of them is a ketone. Once I have one answer, I will move ahead so that we will not waste too much time on unnecessary things. Okay, so quickly do that. A and B, which one is an aldehyde, which one is a ketone? Which one is an aldehyde, which is a ketone? Quickly. Okay. No answers yet. Just one answer and I move ahead. Just one answer. Anybody? Okay. I think I'll just have to continue. The answer basically is A. Why is it A? Yes, A is an aldehyde. Yeah, correct. Good. Chukwuebuka Stanley, Idowu. Yeah, correct. Good. Now, why it is A is simply because that carbon atom is occurring terminally. And once you have those situations, automatically you are dealing with an aldehyde. Okay, let's leave that. Now, I would like to briefly I gave you guys some links to go and look up some videos. But I just want to talk about naming in a very brief manner. Now, when you are naming, we've talked about order of priority. Let's say, for instance, but before we get to that, there are majorly three parts of the name. You have the infix, the infix. Sorry, let's start with the prefix. Let's take it in the direct order, the major order. You have your prefix, you have your infix, and you have your suffix. Okay, so let's look at this. If we consider this particular guy now, the prefix is what indicates the substituent. Now, when I say a substituent, I am simply talking about anything that is an attachment to the main chain. See what I mean? Imagine I have a chain of carbon atom like this, and then you now find out that there is something attached here, maybe like chlorine. You find out that this particular guy is the parent chain of carbon atom, while this guy is the substituent. Anytime we are indicating a substituent, it is written as a prefix. It is written as a prefix. Okay, now another twist to this prefix. Imagine, for instance, we have this and we have OH here. I mentioned in yesterday's class that in this case, you now have the hydroxyl group and you have the carboxylic group. These are two functional groups, but you have to follow what we call the order of priority. And the order of priority in this case has that the carboxylic group is higher in priority to the hydroxyl group. So which means that if I'm talking about my parent chain, the carboxylic group is part of the parent chain. Which means if I'm numbering, I'm not going to be numbering from this side. I'm numbering from this side because the carboxylic group is the highest priority here. So I'll give 1, 2, and 3. Now, if I want to name this compound, first of all is that 1, 2, 3 carbon indicates prop. And when you have prop, because this is a carboxylic or acid, it is going to be propanoic acid. Now, having this as propanoic acid, what am I now going to do? I need to indicate the position of OH. Because hydroxyl is not a major functional group here, I will just attach it as a substituent. Now, if you notice, it is now a substituent. And if I'm now naming the compound, I need to indicate the locant. The locant is number 3. So I will say 3-hydroxy propa. Noic acid. Okay, now imagine I was to name this one. So this is 1, 2, 3, 4, 5. 5 indicates spent. When you are giving number, you start from the side closest to a substituent. But before you consider the substituent, you need to consider the order of priority. There is no major functional group here, so we are just going to consider the substituent. You get. So if you are giving number, we are not going to start from here. We're going to start from here because this side is closer to the substituent. If there was a functional group, we will now consider the functional group before the substituent, but there is none. It's just carbon and then chlorine as a substituent. So let's do that. So this is going to be 1, 2, 3, 4, 5. In this case, if you have to name this, this is going to be the parent chain is spent. 5 carbon indicates spent. And once you say that, the implication is that it's a pentane because it's all single bond. So it's going to be pentane. Now, because this particular chlorine is on number 2, we will say 2-chloropentane, and that's basically the answer to this question. Now, this is that about substituents. Substituents are indicated as prefixes to the parent chain. Whenever you talk about a substituent, where it is indicated is as a prefix to the parent chain. Okay, before I let this go and we continue, I'll just give you one to do. Just try naming this substituent. What do we think? Based on what I just said, I talked about, okay, look at this guy. Double bond O, OH. If I say you guys should name this guy, or yeah, what's the name of this compound? Let's try. Or everybody, try, attempt. What is the name of this compound? What is the name of this compound? Yes? I just need one answer and then I continue. Okay? Just name the compound, one answer, and I continue quickly for want of time because I want to utilize this time in the best possible way. Okay, so just one answer and I continue. There's a little bit of time lag between where I am and where you guys are because I think the distance far die. Oh yeah, Mona do time no deal. When I don't hear question, oh yeah, give me answer. One answer. One answer. What do we think is the name of this compound based on what I just said? Okay, so what do we think? 2-chloropropanoic acid, correct, and that's the answer. Very easy, right? Good. Now let's continue. Now that is that about your prefix. Your prefix tells you the substituent. Now the next part I'm going to quickly talk about is the infix. The infix is the part that tells you the number of carbon atoms in the parent chain. Carbon atoms. And I think I have outlined, I'm going to put out a link. Let me see if I can quickly get the link so that I'll put out the link on naming so that you can easily access these things. Okay. I sent the link yesterday. I don't know how many of you were able to watch it, but I'm probably before the end of the class I'll put out that link. But let me just highlight some of the things that we need to know. Now, there are popular infixes that must be known, and at least in your level, you need at least to know the number of carbon atoms or the infixes for carbon atoms 1 to 30. You get. I will start with number 1. When you see 1 carbon, it means met. When you see 2 carbons, it means et. If you see 3, it means prop. If you see 4, it means boot. If you see 5, it means pent. When you see 6, it means hex. When you see 7, it means hept. When you see 8, it means oct. When you see 9, it means non. When you see 10, it means deck. What if you see 11? It means on deck. If you see 12, it means do deck. If you see 13, it means tri deck. 14 is tetra deck. Now, did you just notice something that when we got to 10, when we got to 10 and 1, we did not write 10 and 1, we wrote 1 added to 10. This is do deck, 2 added to 10. Tri deck, 3 added to 10. Tetra deck, 4 added to 10, which means 15 will now be 5 added to 10, which is penta deck. 16, hexa deck. 17, heptadec, 18 octadec, 19 nonadec, and finally 20 is what we call the IQOS. Okay, so sorry, that's the wrong spelling. IQOS. Let me put 20 somewhere. Okay, so 20, let's just use that. 20 is the IQOS. Now, what does this mean? Imagine, for instance, I'll just use a simple illustration and then move ahead. Imagine, for instance, I have this 1, 2, 3, 4, 5. This is 5, and I'm noticing that I have OH. Now, whenever you see C double bond O, I told you that the carbonyl group is C double bond O, and if you see C double bond O, it simply indicates an alkanal or an alkanone, which is an aldehyde or a ketone. Another name for alkanals is aldehyde. Another name for ketone is alkanones. In this particular, can someone tell me, is this structure an aldehyde or a ketone? Based on what I've said so far, so that we'll know if we are following. Is that an aldehyde or a ketone? Aldehyde or ketone? Is this an aldehyde or a ketone? Just one answer, I move ahead. Is this an aldehyde or a ketone? One answer and I move ahead. Okay. Okay, so yes, just one answer and I move ahead for want of time. Okay, good. Chukwuebuka Stanley, correct, that's an aldehyde. Now, why it is simply an aldehyde is because we know there is a terminal carbonyl group. Once you see terminal carbonyl group, just know it's an aldehyde. Now, let's name this aldehyde. It's very simple. It has 1, 2, 3, 4, 5 carbon atoms. And 5, when you have 5 carbon atoms, it's pent. Now, this is pentan. Pentanal. Why is it a pentanal? Aldehydes are alkanal. So this is pentane alkanal. But instead of calling it pentane alkanal, you just say it is pentanal. If, for instance, I add an extra carbon atom, this becomes hexanal. If I add an extra carbon atom, it becomes heptanal. So just have that in mind that you are naming it just heptane alkanal, pentane alkanal, but you don't just say heptane alkanal. That's like the old system of naming, and it is no more practical in use now. You get now. However, I would like to advise you, especially those of you that are writing, that UNN students, go and look up those common names. The common names to all these numbers, all these the asset group, the uh the steric group. When you say oleic, what does it mean? And all these things. Just go and look it up. I'll highlight some of them, but it's important that you note these things because some of the times they might not use your normal names. They will not use the IPAC names I meant to say. They will use the common names you get. So just go and look them up. What does it mean when you say valeraldehyde or things like that? We'll get to discuss those things. So, but for now, just note that when you are naming, if you are able to count the number of carbon atoms, it makes everything easy. Now, if you have an alkanal or an aldehyde, just end it with al, and that's the compound. If it's an alkanoic acid, just put oic, and that's the compound. And basically that. I'm just rushing through because initially you are supposed to look through this study before today's class. Now, with that established, we come to the final part of the names, and that is suffix. This is where we would round it off. Now, the suffix, there are different compounds. Once you have an alkane, for instance, how do you know an alkane? It is a hydrocarbon that only contains single bonds. The suffix for alkane is simply ane. So you have that. If it is an alkene, it has double bond and it will end with ene. So when I draw this has 2 carbon atoms, et. Because it has a double bond, it's an alkene, so ethene. Finish. And that's that basically. Okay. If I happen to have alkyne, alkyne has triple bonds and it ends with yne. So when I draw this is what? Ethyne. Why? Because et indicates 2 carbon atoms and triple bonds is indicated by the suffix "-ine". Simple. Okay. Now imagine, for instance, I have an aldehyde. An aldehyde is indicated by the suffix "-now". In some textbooks, they could use "-al". Anyway, let's use "-al". What does that mean? If I draw this 1, 2, 3, and I put a terminal carbonyl group, this is going to be prop. Because there are only single bonds, it's going to be propan, like propane, propane aldehyde. But I'm not going to say propane. I'm simply going to put "-al" at the end of it, and it becomes an aldehyde. This is not just a propane. It is a propane that has an alkanal. And you have that. If I want to indicate it, I should just remove the E and put "-al". Okay, imagine I had something like the ketones. The ketones are also referred to as alkanones. I know I'm giving their other names. I presume I'm not fast. I'm trying to be as slow as possible. I'm trying to cover as many things as possible. That's why I'm rushing it a bit. You get. So the ketones' other name are alkanones. And when you want to indicate them, you indicate them by ONE. So imagine I have something like this. 1, 2, 3. First of all, I know that this is a ketone because this C double bond O is non-terminal. Now, how many carbon atoms do I see? I see 3. 3 is prop. It's only single bond, so it's propane alkanone. But I'm not going to put the E. Instead of putting the E, I'll now put this suffix here. What is the suffix? Propanone. You get. Now, it becomes tricky. I'm just going to talk about this now. In naming, it's important to note where the functional group is found. Why we don't need to indicate that of alkanal is because it is always on number 1. You get. If we were to number this thing, we'll start from here. 1, 2, 3. Because this is the functional group of higher priority. You get. But in this case, we're not going to consider which one is closer. Now imagine I had something like this. 1, 2, 3, 4. Okay. So what do we think is this compound? Is it an alkanone? Let's try naming it with what I just taught you. Let's give suggestions so that I can move ahead. Let's try naming this. Yes. Once I have one answer, I would move ahead. Uh-huh. Okay, just one answer and I move ahead. Okay, Idowu, you are correct. Butantu-on is correct. Now let me explain why it is Butantu-on quickly so that everybody will understand. Now remember we used to allocate numbers. It's important you already know this now. If we are allocating numbers, we're going to start from the side closest to the functional group of highest priority. And we know that the only one here said is just alkanol. So which means you are going to start from this side, this closer. So this is number 1, number 2, number 3, and number 4. Now, if we have this is all single bond, so this is going to be butane, but we're not going to put the E. Instead of saying butanone, we need to show where the alkanone is. It's on number 2. So we are going to put butan 2 on, and that's that. If you had something like this, okay, let's try this one out. Imagine we had 1, 2, 3, 4, 5, and we have this. Oh yeah, let's try naming this particular guy. Everybody attempts naming this particular guy. What is it going to be? Where are you going to start naming? Okay, you know the numbers. Anywhere you start from is still the same thing, but name it. Oh yeah, name. Let's see. Let's see. Give me one answer and I continue. Okay, one answer and I continue. So just one answer and I move ahead. There's no sign. Quickly. Yes, Butan 2 is correct. That should be Nancy commenting. Okay. Okay. Pentan 3 on. Yes, Pentan 3 on is correct. And I move ahead. Okay, very good. Now, Pentax. What's Pentax? Okay, Stephen. Probably that's the typographical error, I guess. Okay, let's just continue. Now, to name why did we say it's Pentan 3 on? If you give numbers, anywhere you start from, it will still be the same thing. So give me numbers. This is 1, 2, 3, 4, 5. So this is going to be pentan is on number 3. So it's 3 phone and so on and so forth. Okay, so that's that basically about naming these things. Now, the other ones, I'm just going to highlight the other ones because they are important, and I noticed that you might see one or two things about them. So the other one I'm going to talk about is alkanols. The suffix for alkanols is ol. Have that in mind. The suffix for alkanols is ol. The suffix for alkanoic acid is oic. The suffix for esters. Why I'm mentioning this is because when we get to lipids, we notice that most lipids are actually esters, and that is OH. So you have that in mind. Okay, so you can go and review the study I gave you guys earlier. It will help you understand this better because I'm trying to rush this through so we can talk about the key things. Okay, now having highlighted these things about organic name, the other thing I would like to say is there are some funny will I say yes, not funny anyway, but there are some things that or some different ways of naming compounds that are not very contemporary, as I just said. For instance, now, anytime you see benzene, benzene ring attached to a substance, that benzene ring automatically becomes a substituent. I take it again. Anytime benzene ring is occurring as a substituent or is attached to a substance, it is more or less referred to as the substituent. Now, if benzene is considered as a substituent, eh, it is not referred to as benzene, it is referred to as phenyl. It is referred to as phenyl. Okay, so let's explain what we mean. Now, imagine, for instance, you have, let's go back to yesterday, we talked about capylene as one of the naturally occurring, capylene, as one of the naturally occurring alkynes that you have, and we said that it has an antifungal effect. Please take note of this because if you just ask capylene, which of these is a naturally occurring alkyne, something like that. Okay, now we now said that if we're looking at the structure of capillin, we're going to have this. One, two, three, four, five, six. You see number two and number three, number four, and number five. Okay, now let's look at this for instance. Okay, no, it's an ion, triple bond. Okay, now can anybody tell me, can you outline the functional groups you can notice in this compound? Give me the functional groups you can notice in this compound. Anybody? Just give me anyone. First of all, is that I can see the aromatic, which is the phenyl group. You get what I'm saying? What else can we see? Is this C double bond O supposed to represent an alkanal or an alkanone? If you remember in the last class too, we said that any junction indicates a carbon atom. So please, this is a carbon atom, 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 this is a carbon atom. So yes, can we give us the major functional group here? What is the major functional group here? Yes, what functional group is predominant in this case? Okay, just one answer and I just move ahead. Okay, an alkanone is predominant here. Now let me explain why the alkanone is predominant. If you look at the screen, we said that when you see C double bond O, and that C double bond O is in between carbon atoms, that is non-terminal, automatically is an alkanone. So which means this particular compound is an alkanone. Now, if you look at every other thing attached, going back to yesterday's class, alkanone is the highest, that is, it has the highest priority in this compound. Which is to say, we are to consider this compound as an alkanone because if you look at all the substituents, alkanone is the highest in priority. That's why it's important that you have reviewed yesterday's class. Because alkanone is the highest in priority, we are going to name this compound as an alkanone. And every other thing is going to be a substituent, including this particular benzene. So let's put the name together. First of all, is that the name is now going to be based on the longest continuous chain. And the longest continuous chain is 1, 2, 3, 4, 5, 6. Now, this is hex. Hex. But you notice that this hexene, if we're going to give numbers, we are not going to start from here. Why? Whenever you are allocating numbers, you start from the carbon atom closest to the functional group of highest priority. And we all agree that alkanone is the highest functional group here. So we're going to give numbers 1, 2, 3, 4, 5, and 6. That is why it is hex. That's for the straight chain. Now, please listen. Hmm? Once you notice a double bond or a triple bond, you need to show that it is there. We are noticing a triple bond between 2 and 3, and also between 4 and 5. To indicate them, you take the locant, the lower locant. That is between 2 and 3. The one you're going to take is 2. So this is hex 2. Now we're noticing another one between 4 and 5. So we'll also indicate it. Hex 2, comma 4. How many triple bonds do we have? Diene. Are we there? I take it again. We are indicating the triple bond before we come to the alkanone side. So this is going to be hex number 2 and number 4. Why? If you have a triple bond or a double bond between two carbon atoms, you take the locant of the lower value. That's why we took 2 here. And when we came between 4 and 5, we took 4. How many of the triple bonds? We have di, and it is indicated by ine. Now we are not going to end it with E because this is an alkanone. So this is going to be ONE. So if we look at it now, this is going to be hex 2, 4 diinone. We are not done with naming this compound. Because this particular guy is a substituent, it is going to be written as a prefix. And I told you, anytime benzene is written as a prefix, we refer to it as phenyl. So the name of this compound is going to be phenyl hex 2,4 diinone. And that is the name of this compound. I said this is capillane. I'm just trying to illustrate or bring in different dimensions of naming. I will give you a simpler one and then explain a simpler one. I'll explain a simpler one and use that simpler one possibly to make it clearer. But I just wanted to talk about capillane because I saw this in your textbook. Okay, now giving you a simpler structure. Imagine, for instance, we had something like this. We had something like this. Okay, and OH is here. In yesterday's class, we established that alcohol is represented by OH, and alcohol has a higher priority to double bond, which means because this OH has a higher priority, this compound is going to be an alcohol and not an alkene. Once you want to name the compound, check for the functional group of highest priority. If you find out the functional group of highest priority, the compound coincides with that functional group. So you have a double bond, which is alkene, and you have OH, which is alcohol. But alkanol is higher in priority to alkene. So this compound is an alkanol. We have all agreed. Now, if we are going to give numbers, we are going to start from the side closest to this higher functional group. So this is 1, 2, 3, 4, 5, 6. Now let's circle this. If we happen to circle this out of our parent chain, let's now name this compound. Now, this is 6, meaning hex. But we are noticing a double bond between number 4 and number 5. So this is hex 4 indicating the double bond. Now, it is not going to end with E, but it's going to end with O. But where is this O located? It is located on number 2. So this is going to be hex 4 in 2 O. Confusing? I hope this is understood. If it's understood, just indicate. Just indicate quickly so I can move ahead. Indicate quickly so I can move ahead. Indicate quickly so I can move ahead. Okay. Obuchioma, God, I beg. Okay. Don't worry. I will go to simpler ones and take it from there. Okay. Uh-huh. Okay. Okay, so Chinkata says he or she is following. I don't know if you're male or female. Chinkata is following. Any other person? Just one more indication so I can move ahead. Just one more indication. Okay. I will give you another one. A simpler one. You get. Hello there, what is okay. Okay, so one more indication so I can continue. Okay, so let's try one more before I go to questions in your listing. Imagine you have this. Look, you have this. You have this. Eh? I say you have a double bond O, then you have fish, then you have here. Okay. Okay. All right, let's look at this guy now, for instance. Now, first question I'm going to ask you is this guy an alkene or an alkanal or aldehyde? Let's answer this question. That's the first thing you need to answer. And how will you answer it? Check for the order of priority. Okay, let me even rewrite the order. For 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 those that have not been to my class, order of priority, alkanoic is the highest. Then ester. After ester, amide. After amide, aldehyde. Aldehyde. Then ketone. After ketone, alkanol. After alkanol, amine. After amine, alkyne. After alkyne, alkene. After alkene, any other substituent then alkane. Okay, so let's look at this now. So, based on what I just said now, who is this compound? Is it an alkene or an aldehyde? Remember, I told you for you to note which one is which, just check the one that is higher in priority. So according to Idowu, this is an alkanal, and that is what it is. Why is it an alkanal? If you look at the order of priority that was given, hmm, aldehydes are higher in priority to alkene. So automatically this makes this an alkene. Sorry, automatically this makes this an aldehyde because aldehyde is higher in priority. Now we are going to impute the position of alkene, you get, and I'm going to show you how to do that. You get what I'm saying? So that it becomes easier. I'm just rushing through. I don't want to overemphasize naming because that's not the essence or major thing in this part. I've noticed in your questions that they don't overemphasize naming, but it's important to know it. Now, how many carbon atoms are here? One, two, three, four, five, six, seven. So that is hept. Hept. Now, we would need to show the double bond position. It is between number 4 and number 5. So this is hept 5 ene, but we're not going to put the e because this is not a normal alkene. This is an aldehyde which ends with al. So this is going to be hept 5-ene al. Finish. Now we don't need to put number 1 because every time you have an aldehyde, it's always going to be there. Okay, you guys should try this one. Imagine I have this 1, 2, 3, 4, 5, 6, 7, and I have this, eh? And then I now come and have this. Oh yeah, let's try naming this compound finally before I get into the other part that we should discuss. So we'll leave this. There's no much time. Oh yeah, oh, quickly. Let's name this quickly so I can go into the other part. I'm actually supposed to emphasize. Yes, what do we have? What do we have? What do we have? Hept for now. Okay. Choma, I think is let's check it again. This is not going to be an alkanal. Do you know why it's not an alkanal? Let me remove this thing from the screen first of all. Sorry, let me remove this from the screen. So let's understand first of all that this is not an alkanal. This is not an alkanal, this is an alkanone. I've told you people now that the only time you call it alkanal is if it is occurring on the last carbon. That is either here, here. If C double bond O is here or here, that is when it occurs terminally. That's when you say it's alkanal. But when C double bond O occurs any other place that is not on these edges, that's when you call it alkanone. So with this understanding, can you people review your answer and tell me what you think? So if you are giving number now, this is going to be 1, 2, 3, 4, 5, 6, 7, 8. I wonder why you people said hex. Please count this thing well. Oh. It's 8 now. It's 8. So try again before I give you guys my final. Oh, yes, yes, yes. Sorry. Oh, no. Thank you very much. Choma, I made a little mistake here. Thank you. Sorry. Thank you for that correction. This is supposed to be yes, this is not supposed to be the actual name. This is not this is yeah, thanks. Thanks. Yeah, it's between 4 and 5, so we are taking the lower number. I forgot that. So this is going to be help for now. Thank you very much. I omitted that. Okay, yes. So yeah, it shows we are following though. So let's continue. So what do we think? Oct 6 in 3 own. Okay. Yes. Oct 6 in own. You forgot to indicate the presence of the position I meant to say of the carbonyl. You did not indicate that. Ido Akinbola. But yeah, Nancy Godson, Nancy, you're correct, basically. Okay. Um okay, yes, we have that. Now let me just explain that so that we'll move on to other parts quickly. Okay, now explaining this, very simple explanation, as we all know now. Counting from here is oct. This is 7, 8, and this is oct. But we need to show the presence of double bond. This is between 6 and 7, so oct 6, you take the lower one in. But then we will not put own because we need to show where the own is located. Own is located on number 3, so this is oct 6 in 3 own, and that is the name of this compound. Now I am going to move slightly away from naming. Let's go to your past questions and see if we have anything on naming and try out just one question there. Okay, yeah, I think we have something on naming. Okay, yeah, so let's look at this structure. What do we think is that's the answer to number 82? The answer to number 82. What do we think is the answer to number 82? I'm going to describe that. 82 has a little the diagram. I think I'll have to redraw this diagram so that we would not be confused because there's a little shift in the position of that C double bond. So it's going to be CH2. Okay, I'm just going to redraw the whole thing because there's a typographical error in that diagram. If you use that diagram, you are going to have, let me just redraw everything so that you see what I'm saying. C H. Okay. So let me just redraw it. Okay. Okay. So if we are to redraw that, that's going to be 1, 2, 6, 6, 6, supposed to be 5. Uh-huh. 6, 1, 2, 3, 4, 5. Okay. Okay. So let me redraw the diagram just to make it easier for us to understand. Okay, so I'm redrawing the whole diagram so that we would understand what was happening there. Now, the diagram is originally supposed to be CH3, CH2, CH, CH3, C, CH3, H, C, double bond O, H. Okay, this is what you're supposed to have as the diagram. Okay, let me confirm, pull it up again and see. Confirm what I'm trying to. Okay, if you move that forward, okay, this guy was moved. Yes, alpha beta. Okay, good. Okay, now let me explain some things about this. First of all, is whenever you notice a particular functional group or an attachment to a particular compound, first of all, the main functional group here is aldehyde. This guy. If you cut it out, using the common naming system, they don't use number one, number two, number three. If I to use number one, number two, this is going to be simply 2 and 3 dimethyl 1, 2, 3, 4, 5 pentanal. You get, but they said what is the common name, not the IUPAC name. So let me teach us one or two things about common name. First of all, in common name, we should note that when you say 2 carbons, it means acet. When you say 3 carbons, you are basically looking at the term propino or propano. Yes. So you're looking at propino, propino as 3. When you say 4, in common name, you are looking at butyl or butry, something like that. When you say 5, you are looking at val. You get. So the implication is that most times vala or something like that. And when you say something like 18, you are looking at steric. This is or ster. That's like 18. You get 18. I'm just giving you this common name, so you just have this in mind. So we'll be able to answer this question. Now, this is the first part. Other common names, you can go and look them up in your textbooks. But for this question, I just want to answer it and show you something. Now, they don't look number or give the locants from the functional group. How it is being numbered is once you notice the major functional group, you leave that functional group and start allocating locants from the next one. The carbon atom closest to the functional group is called alpha. The next one is called beta. The next one is called gamma, and so on and so forth. So just have this in mind that when you are giving a common name, they don't give numbers. What they give is Greek numerical values. And the Greek numerical values do not necessarily start from the carbon atom that has the functional group. It starts from the carbon atom closest to the functional group. And in this case, this guy is the alpha carbon. Why? Because it is closest to the functional group, carbonyl. If I had something like this now, you will notice that this guy becomes alpha. Why would this guy become alpha? Because it is closest to the functional group is carboxylic. If I have this now, and I have OH here, I'll have alpha here, and this is also alpha. Are you get what I'm saying? So any carbon atom that is closest to the carbon carrying the functional group is what we refer to as the alpha carbon atom. So let's come back to what we are doing. Sorry, is there any confusion so far based on the alpha and beta positioning? I would like to clarify that before I continue. Yes, let's quickly comment. Oh my God, this thing has been blocking the screen. I'm so sorry. I will re-explain. Okay, I'll re-explain because the screen was actually blocked initially. Okay, so re-explaining, um, I did not know that the screen was blocked. Okay, so re-explaining, I said that once you have the functional group, you don't number or give locants like number 1, 2, 3 in common name. In common name, you use Greek numerical values like alpha, beta, and gamma, and the rest of them. I don't think they're going to ask you guys more than alpha, beta, gamma. You get. And how is this given? You don't start from the carbon atom bearing the functional group. You start giving the numbers or the Greek numerals from the carbon atom closest to. the functional group. This is carbonyl. C double bond O is carbonyl, and that's the major functional group here. So when we are going to start giving the group numerical values, we'll start from the closest carbon. So this is alpha, this is going to be beta. Are you getting? This is gamma, and that is that basically. So if, for instance, let me just put out another example. If, for instance, I had 1, 2, 3, 4, C double bond O, OH. This carbon is the one attached to, or this is the carbon of the functional group. This is carboxylic, which means I'm going to start from here. This is alpha. This one will now be beta. This one will now be gamma. Are you getting? It's not like the normal one where you give number 1, number 2, number 3, number 4, number 5. So the common name for this compound, having said this, as I said, is you need to understand that these common names have different. They are different. You get? This is Valer. Now, when you consider 5 carbon atoms in the parent chain, 1, 2, 3, 4, 5, this is the continuous parent chain. It is 5, meaning that we're dealing with Vala. And because this is an aldehyde, how they are named is Valer. Oh no, the parent chain will now be named as valeraldehyde. That is the parent chain. Why? Because the common name for 5 carbon atoms is Vala, and once this is an aldehyde, it becomes a valeraldehyde. If this was an acid, it becomes valeric acid. If this was an alkanone, it becomes valeranone. If this, for instance, was an alkane, it becomes valerane, and the rest of them. But the point is, because it's an aldehyde, 5 is Vala in common names. And because this is basically an aldehyde, it becomes a valeraldehyde. Basically, that is the indication of the 5 carbon atoms in the parent chain. Now, this methyl group here and this one here are both substituents, and we're going to indicate their positions. The first methyl is attached to an alpha carbon. I told you an alpha carbon is the carbon atom closest to the functional group. A beta carbon is after the alpha. Are you guess what I'm saying? So if we are to name this particular compound now, we have a methyl on alpha and another methyl on beta. So let's name this. This is now going to become alpha beta dimethyl. Then we put the parent name valeraldehyde. Okay, so if you have this, which option was this in the question? Let's check it out. Let's check it out. Alpha beta dimethyl valer. That is option C. That is option C. You get, and basically that's that. So I presume this is understandable and based on, yeah, I was initially obstructing, but this is, and it's back. Okay, so that's that about naming. I would advise you just go through those studies I gave you guys initially. It would help you in no small way. Now, let's get into another important part of this particular study, and that is your reactions of alkanals and alkanones. Yesterday, we established one fact that is very important. Primary alkanols are oxidized to give alkanals, which will now give alkanoic acid. Secondary alkanols are oxidized to give alkanones, and alkanones cannot be oxidized. So the first point in the general reactions of alkanones and alkanals, number 1, alkanals are oxidized to give your alkanoic acid. And I told you that the enzyme involved in this process is your aldehyde dehydrogenase. I explained this thing in that last video, that dehydrogenation is the same thing as oxidation. So the aldehyde, the enzyme that dehydrogenates an aldehyde is the aldehyde dehydrogenase. Okay, in the case of an alkanone when it is oxidized cannot be oxidized further by any normal oxidizing agent, so you have no reaction here. And please, this is the emphasis for differentiating alkanals and alkanones. Now you will see a question where they will tell you which one of these reagents are used to differentiate alkanals and alkanones, there are three major reagents that you're going to come across in this study. The first reagent is Tollens reagent. In fact, all these things are actually oxidizing agents. Tollens reagent. The second one is Benedict solution. Benedict solution. The third one is Fellings reagent. You can also use acidified KMNO4. Now, the point about it is, if you introduce this to an alkanal, you will have silver coating for alkanals, but in alkanone, no reaction. The simple reason for this is this. Alkanals can be further oxidized, and when they are oxidized, the oxidizing agents will react with them. You get, hence reducing the silver nitrate to a silver metal. However, the alkanals will now be oxidized to alkanoic acid. But because alkanones cannot be oxidized, there will be no reaction. Benedict solution, you have, yes, a brick, yeah, a red. Benedict solution, yes, should be red, basically. Fehling solution is also red. And then decolorization. But in the case of alkanone, no reaction. So to differentiate an alkanal from an alkanone, once they introduce an oxidizing agent to an alkanal, there will be a color change. But if it is introduced to an alkanone, there is no reaction. Why? Alkanones cannot be further oxidized by normal oxidizing agent, but alkanals can be further oxidized. That is the first thing I would like to establish in this class. Okay, so is there any confusion so far? Oh my God, I'm still blocking. I'm so sorry. I did not notice this thing. I've made this mistake twice. Sorry. Sorry about it. Okay. Okay, sorry. I did not notice that. Let me just quickly reiterate what I said initially. Let me reiterate what I said initially. Now, I said that alkanals are oxidizing agents. Sorry, alkanals can be oxidized, I meant to say, but alkanones cannot be oxidized, which means once you introduce any of these oxidizing agents to an alkanal, you have a reaction. If you introduce Tollens reagent to alkanal, you have silver coating. Silver will be produced, and those silver that will be produced will coat the inner walls of the test tube. If you introduce Benedict's solution, you have a red color. If you introduce Fellings reagent, you also have a red color produced. In the case of KMNO4, it will decolorize KMNO4. It will decolorize it from purple to colorless. Now, because alkanals can be oxidized, that's why they will react. But alkanones cannot be oxidized. So for all these reagents now, there will be no reaction. That is the first thing I would like to establish. Alkanals can be further oxidized, and because of that, they can react with oxidizing agents. And if you look at, just all you need to know is the color change for oxidizing agents. Tollens reagent will produce silver, so alkanals will produce silver. Benedict solution will produce red, so alkanals will produce red. Fellings reagent will produce red, so alkanals will also produce red. KMNO4 is changed from from purple to colorless when it is oxidized, so which means alkanals will decolorize KMNO4. However, because alkanones cannot be oxidized, there is no reaction for all of them. No reaction, no reaction, no reaction. So you just have that. That generally speaking, anytime you have an alkanal and an alkanone, the first thing you need to note is alkanals can be oxidized to give alkanoic acid, while alkanones cannot be oxidized. So you have that. So if you're asked to differentiate, these are the reagents that are used to differentiate alkanals from alkanones. Okay, so I hope at this point it was understood. Has it been clarified? Okay, so just quietly indicate so we can move ahead quickly for want of time. Mhm. Okay, so that's that basically about that first reaction. Alkanals can be oxidized, alkanones cannot. So if you introduce oxidizing agent to alkanals, all of them will react, but in alkanones there will be no reaction. And I've given you the different color changes that occurs for all of these oxidizing agents, and that's what you need to know. Okay, then we move ahead to the next one. The next reaction that is important you understand, the next reaction that is important you understand is the reaction of alkanals and alkanones with alcohol. Very important. Now I'll start with the first one. Alkanal plus alcohol. Now what it is going to give is what we call a hemiacetal. If you now have excess of the alcohol, this hemiacetal will now be converted to an acetal. So let me explain what I mean by that. Okay, I'll give you a reaction. I'll give you a reaction. An alkanal, let's use a very simple alkanal. Let's use CH3, CO, and then H. This is what we refer to as ethanol. And then I'm going to react it with a simple alcohol. Let's use methanol, CH3OH. Now let me tell you what actually happens in this process. Whenever an alkanal or an alkanol, you know the alkanals are aldehydes. Please note, alkanals are aldehydes. They are the same thing, for some of you that might have issues. So the other name, this is ethanol or acetaldehyde. You know, I told you acet indicates two. So this is acetaldehyde. This is methanol, and the implication of this statement is that it has one carbon atom. Now let's move ahead. Now, what happens in this reaction is quite simple. First of all, is hydrogen will move from here and attach itself to this oxygen here. And once it does that, this bond will be broken. And then secondly, O with CH3 will now move and attach themselves here. So what do I mean by that? This particular second bond will be removed once hydrogen attaches itself to oxygen here. And what is going to happen is this. You have CH3, C. Remember I said that one of the bonds will go away and you have just O. Instead of double bond O, it will now be single bond O. But I told you that hydrogen will now come and join the oxygen. So you have hydrogen here. And then it continues. Remember there was a hydrogen here before, so we just put down the hydrogen. Now I told you that this OCH3 remaining will just attach itself here. And this is what we call a hemiacetal. Why is it a hemiacetal? An acetal basically has two ethers attached to the carbon chain. So when I have CH3 and I have OCH3 and another OCH3, this one now is a complete acetal. Why? O alkyl group, O alkyl group. But this one that has O and alkyl group, but here you have O and hydrogen, is hemiacetal. That is to say, it is not a complete acetal. I take it again, that a hemiacetal has one alkoxy. When I say alkoxy, alkoxy is when you have an alkyl group attached to oxygen and one hydroxy attached to carbon atom. When you have hydroxy is OH, alkoxy is alkyl and oxygen. Once you have this is what we refer to as a hemiacetal. But when you look at an acetal has two alkoxy attached to it. Okay, but for now, I'll come back to this. Let's consider an alkanone reaction. If you are dealing with an alkanone will react with an alcohol. Instead of giving a hemiacetal, it will give an acetal directly. Remember, I told you acetal has two alkoxy. So I'm going to use an alkanone. The alkanone I'm going to use is the simplest alkanone. The simplest alkanone existing in nature is acetone. So just have that in mind. The simplest alkanone existing in nature is acetone. Acetone is the same thing as propan-2-one. You get? I'm giving you the common name. You get? Basically. You are seeing three. The number of carbon atoms that are counted, they did not include the carbon of the functional group. That's why they refer to it as acetone. That's the common name anyway. Just have that in mind. But the IUPAC name is propan-2-one. Now, reacting this with methanol. So this is going to be H3, and this is going to be H3. Now let's see what happens. First of all is this hydrogen. Okay, Let me make a little bit of a correction here. Okay, so yeah, I was just trying to confirm something. Okay, sorry, there was a little glitch in the listing, but we are back. Okay, I just wanted to make sure that everything is going well. Now, having said that, the point is probably you will not get to discuss these reactions in details. You get, so instead of confusing you, that alkanals and alkanones, when they react with alcohol, they produce hemiacetals and acetals. Are you getting what I'm saying? Just have that in mind, that they produce hemiacetals and acetals basically. To avoid, I just checked your past question and noticed that in the questions did not emphasize the reaction. You get, so I don't want to overstress something that is likely not to come out. Now let's move ahead with what we've been doing. Now, having discussed this particular point, these are the two major reactions I noticed that are are prevalent in the the study you guys have in your bio 151. Number one, as I said, is the oxidation. Oxidation of alkanals will not give will give us acetic alkanoic acid, but oxidation of alkanol will not give us anything. That is number one. Secondly is reaction of alkanals and alkanones with your alcohol will give us hemiacetals, which is further reacting to give your acetals. Are you getting what I'm saying? So just have that in mind. Alkanals and alkanones react with alcohol to form hemiacetals and acetals. You get. It is not going to be emphasized. As I said, some of these things are not things you're going to do here. We are going to study it in details in your second semester. So I don't want to depress that so that we'll not be wasting our time on important things. Now, I think the next reaction we need to talk about is this reaction. We talked about it yesterday, but let me just re-emphasize it. Primary alkanol, when it is oxidized, it forms alkanal, which means when it is reduced, it should give. So have that in mind. The alkanal on reduction will now give primary alkanols. Alkanones on will now give us secondary alkanols. I'm just saying this. We did this yesterday, but I'm just saying this for the sake of those of you that were not here. So just note these three major reactions because that they are the major reactions you are likely to see with respect to this exam. Okay. Now, for want of time, I want to get into carbohydrates immediately. You get. I might be saying one or two things with respect to this particular guy. But for now, let's get into carbohydrates. Now, when you talk about your carbohydrates, the very first thing I would like you to take note of or understand about carbohydrates is that carbohydrates are basically organic compounds that contain carbon, hydrogen, and oxygen, in which the ratio of hydrogen to oxygen must be 2 is to 1. So you have an X here. Okay, let me rewrite. Once you consider a carbohydrate, the three elements in the carbohydrate are carbon, hydrogen, and oxygen. But the differentiating factor is that hydrogen to oxygen ratio must always be 2 is to 1. Imagine you see something like this and you see C6H10O5 bracket 23. Is this a carbohydrate? Yes. Why is it a carbohydrate? You have carbon, you have hydrogen, and you have oxygen. And the ratio of hydrogen to oxygen is 2 is to 1. Why? 10 is to 5 is still 2 is to 1. If I write something like C12H22O11, is this a carbohydrate? Yes. Why is it a carbohydrate? The ratio of hydrogen to oxygen is still 2 is to 1. So if, for instance, you are asked to define a carbohydrate, you will not be asked to define. But if you are asked to, what is the defining factor, or you are asked to indicate what is that thing that you will see and you know that this is a carbohydrate, just note that it is the ratio of hydrogen to oxygen. And what is that ratio going to be? 2 is to 1. A carbohydrate is any organic compound that contains hydrogen, carbon, hydrogen, and oxygen, in which the ratio of hydrogen to oxygen is how many? 2 is to 1. So how do you indicate it? Look at hydrogen, look at oxygen. Once you check it out, you will know which one is carbohydrate by looking at the ratio. Okay, imagine I give you this compound. Now, let's look at the compounds I'm going to put out. I have I said which one of these is not a carbohydrate. I have C6H12O6. I have C5H10O5. I have C2H6O. I have C12H22O11. So which one of these is not a carbohydrate? A, B, C, and D. Okay, let's quickly answer. So we'll move ahead. There's no time. I want to just touch carbohydrate and lipids and then see how far we'll go. Yes. Which one of these is not a carbohydrate? Which one of these is not a carbohydrate? Which one of these is not a carbohydrate? Okay, yes. So which one of them is not a carbohydrate? Quickly. Okay, Mary said C. Yes, and that is that. Why is it C? Because the ratio of hydrogen to oxygen in C is 6 is to 1. Carbohydrates must have 2 is to 1 as their ratio of hydrogen to oxygen. So just have that in mind. Okay, moving ahead. What's the next thing? Now, having said this about carbohydrates, the next thing we need to note about carbohydrates is that carbohydrates are majorly classified. They are broadly classified into three groups. They are broadly classified into three groups. Okay, and what are those groups? Number one is, as you know, the monosaccharide. The second one is the oligosaccharide. And then the final one is the polysaccharide. What are the things to note? Monosaccharide contains the carbon atoms in monosaccharide are 3 to 7. Once you have a monosaccharide, the range of carbon atoms you have in a monosaccharide are 3 to 7. The second thing about a monosaccharide is that it contains just one unit. I will still explain this one unit. Now, the oligosaccharide can contain more than 7. In fact, oligosaccharides can contain 2 to about 9 units of monosaccharide. Now, let me explain what I mean by this. If, for instance, I have C6H12O6, this is a monosaccharide. Notice why it is a monosaccharide. It contains 3 to 7 carbon atoms and it only has one unit. But in the case of your disaccharide, they can contain more than 7 plus. Are you getting what I'm saying? And they usually contain 2 to 9 units. So if, for instance, this is a monosaccharide, and I want to form a disaccharide is when an oligosaccharide has 2. If it has 3, it becomes a trisaccharide. If it has 4, it's a trisaccharide. But the point is that once you are joining mono, 2 monos together, you have di. If you join 3 units of monos, you have trisaccharide, and so on and so forth. But once it is more than 9 units, you now refer to it as polysaccharide. Okay, so that's that basically about that, about the oligosaccharide. So if I have mono plus mono, a very good example, for instance, is if I combine glucose plus fructose, what I'm going to get is sucrose. I will explain this in details. Now, why is this an oligosaccharide? It contains up to 2 units of a monosaccharide. And the monosaccharide here is glucose and glucose. Two of them are 2 units and they will give us what? Sucrose. The type of oligosaccharide that this is now going to be a disaccharide. Now, in your study, we are not going to beat around the bush. The most important oligosaccharide that is being described in this study is your disaccharide. So they do not concentrate on the 3 units, the 4 units, the 9 units. What they concentrated on in your study is the 2 units. So that's where we're going to concentrate. And then finally, you have your polysaccharide. Polysaccharides have 10 units of monosaccharide and above. Now, I'm going to take all these things out and we're going to now take a detailed study individually of these things. Let's start with the monosaccharide. The first thing you need to note about the monosaccharide, as I said, is that the range of carbon atom is from 3 to 7. Now, if it contains 3, you call it a triose. If it contains 4, you call it a tetraose. If it contains 5, you call it a pentose. If it contains 6, you call it what? A hexose. If it contains 7, it is called a heptose. So that is that. Now, but the funny thing about your monosaccharide is that monosaccharides are either aldehyde or ketones. Now, I'm going to use your hexose sugars to explain this. Your hexose sugars to explain this, and it's important to listen now because your understanding of the structure of your hexose sugar will help us when we get into glycosidic bond, the 1,4 alpha, the alpha 1,4 glycosidic bond, and the alpha 1,6 glycosidic bond, the beta, and so on and so forth. So you need to understand this thing now. So listen. Now, when I am considering your popular hexoses, the popular hexoses means that they contain 6 carbon atoms are your glucose, your fructose, your galactose, and your mannose. I'll get to that. But let's draw for these guys. Now your glucose is 1, 2, 3, 4, 5, 6. It has O O H O H H O H O H H H H H H H. Okay. Next one is fructose. Same number of carbon atoms. 1, 2, 3, 4, 5, 6. But this time around, different positioning of the carbonyl group. This is going to be H2OH. This is going to be OH. This is going to be H. Oh, sorry. Mhm. H, 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 H. OH, and basically that. Then the galactose is finally represented as COH 1, 2, 3, 4, 5, 6. Okay, now let's look at all these structures now. I would like to say very important things about this. The first question I'm going to ask, amongst the three of them, which one of them is an aldehyde? Which one of them is a ketone? Based on what we've been studying. So please give me your answers quickly before I continue, because this is where the study becomes tricky. This is where the study becomes tricky. So yes, which one of these is an alkanal? Which one of these is a ketone? An aldehyde or ketone? This is where it becomes tricky. Okay, so put out your answers. Is glucose an aldehyde? Aldehyde, is it glucose? Is it fructose? Is it galactose? Just put out your answers quickly so we'll move ahead. Indicate the aldehyde and the ketones before we move ahead. Okay. Do I have any answer? Okay. For want of time, I am going to move ahead. Now, glucose is an aldehyde. Why is it an aldehyde? The carbonyl group is terminal, so this is aldehyde. Fructose is has a non-terminal carbonyl, so fructose is a ketone. Galactose, on the other hand, is an aldehyde. Why? Because it has a terminal carbonyl. So you have that anyone that has a terminal carbonyl is what we refer to as an aldehyde. The one that has a non-terminal carbonyl is what we refer to as a ketone. So just have that in mind. Now, if you have an aldehyde monosaccharide, basically, if for instance that's 3 carbon, it's going to be the aldotriose. But if it is a ketone monosaccharide, you refer to it as your ketotriose. Basically, I take it again. If you want to indicate these things, for instance, this is a hexose sugar. It has 6 carbon. This is also 6 carbon. This is also 6 carbon. The three of them are all hexose sugars. However, what is the differentiating factor here is that this one is an aldehyde. So it is going to be an aldohexose, while fructose will become a ketohexose. I'm just saying or using this terminology because they could be like, among the three, which one of them is an aldohexose, which one of them is a ketohexose. This is basically how to identify it. The one that is an aldohexose has a terminal carbon atom. The one that is a ketohexose has a non-terminal carbon atom. This is the first differentiating factor about these things. I hope this is clear. If it is not clear, just indicate. I'm going to explain. I want to quickly discuss this thing. Okay, we'll get to that. Uh, Idowu is asking about disaccharides. We'll get to discuss disaccharides, but for now, just get or answer. Did you understand what we just discussed about the glucose being an aldehyde? If you understood, just indicate. Okay, if you understood, just indicate quickly so we can move ahead. Glucose is an aldehyde, galactose is an aldehyde, fructose is an alkanone, which is a ketone, simply because of the positioning. Okay, are we still here? We have gone to sleep? Okay, for want of time, I'll just have to move ahead, basically, for want of time. Now, having discussed these things, I've differentiated the monosaccharides based on the ones that are aldehydes and ketones. Now, there is this other thing that is mentioned. I noticed it in one of your past questions, and that is an epimer. And that is what? An epimer. I will simply describe an epimer. Huh? An epimer is basically, let's consider it with monosaccharide. When you say what is an epimer with respect to, or which two sugars are epimers. We are looking at the two sugars that are only differentiated by difference in the arrangement around only one carbon atom. Once there is a difference in the arrangement around only one carbon atom, we are referring to the two sugars as epimers. Let's say, for instance, we have this. Um, I'll write all the. This is glucose. One, two, three, 4, 5, 6. O, then you have OH, H, OH, OH, OH. Okay, how do I have this thing in my head basically? I just have this constant. If you notice, anywhere OH is, the opposite side is hydrogen. Here that I have OH, the opposite side is hydrogen. Here that I now have hydrogen, the opposite side is OH. Here that I have OH, the opposite side is hydrogen. And basically for glucose is an aldehyde, which means the carbonyl group is terminal. You get. Now, I already have that from this downside. I have three OHs. And then the next one is hydrogen. The only place where there is a change in the position of the hydrogen and OH is on number 3. You know, if we are numbering from here. Good. Okay, so this is glucose. Now, the second aldehyde we are going to consider is galactose. The di 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so the second guy I'm going to consider is galactose. Now, galactose is basically also an aldehyde, and the difference between galactose and glucose is this. Galactose changes the position of OH on number 4. So that is to say, here I'm going to have hydrogen here, and OH will now be on the other side. That is the only difference. So every other thing in glucose is the same thing. This is number 1, this is number 2, this is number 3, this is number 4. In galactose, the difference between glucose and galactose is that there is a change in the position of OH. OH now goes towards the left in galactose. On what carbon? Number 4. So all you need to make sure you know is glucose. From glucose, you can derive galactose. From glucose, you can derive mannose. Okay, in the case of mannose, mannose is also an aldehyde. Mannose is an aldehyde, just like glucose. 1, 2, 3, 4, 5, 6. In the case of mannose, mannose differentiates from glucose on carbon number 2. That is to say, instead of the OH to be on this side, hydrogen will be here, and OH will be on this side. So you have that in mind. So this will change, and this will be hydrogen. This will be OH, 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 H, because OH is here, H, H, H. Instead of H, you're going to have OH. Anyway, you have H on this side, the other side will be OH. And this is, so this is glucose, this is galactose, and this is mannose. Now, I talked about something and I said epimers. Epimers are basically compounds or substances that only differ in their configuration around only one carbon atom. So let's prove that glucose and galactose are epimers. Let me explain. Okay, let's fill this. I said that the only difference on carbon number 4 for galactose for mannose is carbon number 2. So glucose differentiates from galactose on carbon number 4. If you can note this down, it will help you. Glucose differentiates from mannose on carbon number 2, but glucose differentiates from galactose on carbon number 4. So let's fill the rest of them. Here is OH, is the same thing, exactly the same thing. The other parts are exactly the same thing. The only place that differentiates or is different in the case of galactose is carbon number 4, or in the case of mannose is carbon number 2. So you will find out that glucose and galactose are epimers. Why are they epimers? Every other side is the same thing, and it only differentiates only on one. Let's see, for instance, this is number 1, number 2, number 3, number 4, number 5, number 6. Here you have a carbonyl group, correct. Here you have C, OH is on this side for number 2. Two of them, OH is both on that side. In number 3, OH is on the left side. So which means here OH is on the left side, correct. Here OH is on the right side. But in the case of galactose, OH is on the left side. This is where the difference is. Let's see if there's any other difference. Here, carbon OH is on the right side, OH is on the right side. Good. OH is on the right side, OH is on the right side. So which means the only place there is a difference is on carbon number 4. And because it is only on one carbon that you have a difference in the configuration, these two substances are said to be epimers. I hope this is understood. Please, if you understood it, react. If you want me to reiterate, also react. Okay? If you have any reaction, please do that now so that I will know if I need to discuss this concept. Shalom, man. I beg. Say good morning. Land. Okay, yes, I'm still waiting for your reaction. I'm still waiting for your reaction. Should I continue or do I need to re-explain? That's the question. Okay? Mona react to na live class today. I be all of una don't go sleep. Papa. Hmm? Hmm? Okay. I see the way to respond. So Mona talk now. I be una no dey. Okay. Yes, it's still like Josephine Vitalik. Okay, let's continue. Good. Now, go to my status. Now, the having said that, it's important to note that glucose and galactose are epimers. The point of difference for glucose and galactose is carbon 4. Glucose and mannose are epimers. The point of difference between glucose and mannose is carbon 2. I think I have a question. I came across a question. Uh, so that I came across a question like that. Let me see if I can get that. Let's see. I'm not sure. IPAC product vision responsible symptoms. Okay. Enzyme stabilize cellular blah 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 blah. Let me see. Linolate configuration H enzyme motors glucose gives two types of starch. I'm not sure where I saw that question again. OH right side. Yeah, okay. Okay. Question 3. Sucrose contains which of the following is not fatty acids, reaction, ketones, and alcohol. Okay. Okay. Um, I can't seem to find the question. Okay, we'll just move ahead. Probably come back to that some other time. But my point is this: just note that glucose and galactose are epimers. Why? There is only one point or one carbon where there is a difference in the configuration, and that carbon for glucose and galactose is carbon 4. But in the case of mannose, the difference in their configuration is on carbon number 2. Okay, I would like to draw the structure of fructose and you tell me if fructose is an epimer. What do you guys think? Is fructose an epimer of glucose? Let's see. Fructose is C. It has the same structure as glucose, so the only difference is that 1, 2, 3, 4, 5, 6. That instead of the carbonyl to be on the final carbon is here. So you guys tell me is fructose an epimer of glucose? is fructose an epimer of glucose? This is fructose. Okay, so let's talk about that quickly so I can move ahead. Okay, is fructose an epimer of glucose? Is fructose an epimer of glucose? Okay, now I would say no. See the simple reason. Let's look at the structure of fructose. The simple reason is epimers would only differ on only one carbon atom. But if you consider fructose, first of all, is this is glucose. Glucose has C double bond O on number one. But on number one of fructose, it has COH. So there is difference here. Difference here. We come to the second. Second carbon has COH. But this one has C double bond O. Difference here. Difference here. So automatically you've gotten up to two, which means fructose and glucose are not epimers because epimers only differentiate on only one carbon atom. So just have that in mind. Now, having said that, I would now extend it into the next part. We are done with the monosaccharide. We will still come back to them. Yes, I need to do or show you something about the monosaccharide. Now, when monosaccharides are dissolved in water, they actually take a cyclic structure, and I'm going to show you how to derive that cyclic structure. Let's use glucose for instance to do this. Glucose has the straightforward structure as COH. See, I told you that basically what happens here is OH is always on the right side. One, two, three, four, five, six. The only place OH is on the left side, I mean, is when you have your carbon 3. For glucose, every OH is on the right side. You get the only difference is on carbon 3. That's for glucose. You get. So if you know how to get your glucose structure, others can be derived. How? You note that in the case of galactose, the epimer or the place or point of epimerization is on carbon 4. In the case of mannose, is on carbon 2 and stuff. So once you know this, you can derive that particular other structures. Now, having said this, shalom, having said this, sorry, let me just see if I can restore power because power was just lost now. Sorry guys, I went to like put on the generator, so we'll continue. Okay, so are we still here? I had to go and put on the generator so that we will not get confused. Okay. Now, why I want to explain this thing is so that when we get to starch, we would notice that starch is made up of two major polymers, the amylose and the amylopectin. I just want to emphasize this cyclic structure because your understanding of the 1,4 alpha 1,4 branching and the alpha 1,6 branching, the beta 1,4 branching, and so on and so forth, all those things is simply based on this cyclic structure. So please pay attention. If you want to form the cyclic structure, eh, just this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. All you need to do is join 1 to 5. That is all. Join 1 to 5 and make it cyclic. So which means if I start with carbon 1, okay, let me just shift it a little bit. If I start with carbon 1 on this end, this is carbon 1, I'm going to join it to carbon 5. Okay. But before I join it to carbon 5, the thing is that this oxygen here is what is going to be attaching itself to carbon 5. So I have oxygen, and this oxygen will now attach itself to carbon 5. So this is carbon 5. Now, carbon 5, if you remember, is attached to carbon 4. So let's continue the flow. Carbon 5 is attached to carbon 4. Carbon 4 is attached to carbon 3. Carbon 3 is now attached to carbon 2. And carbon 2 is attached to carbon 1. And remember that carbon 5 is also attached to carbon 6 here. And basically that is how it works. So any of the carbon that is carrying the carbonyl group, any carbon carrying the carbonyl group is simply the carbon atom that attaches to carbon 5. You get. And the carbon carrying the carbon of the carbonyl group is what we refer to as the anomeric carbon atom. This is the the little disconnection. Okay. So I take it again. When you say anomeric, anomeric is describing the carbon atom of the carbonyl group. Anomeric simply describes the carbon atom of the carbonyl group. So anytime you are looking at the carbon atom of the carbonyl group, it is the anomeric carbon atom. And I said, if you want to form the cyclic, just take this carbon and link it to carbon 5 and you form your cyclic structure. Now, mind you, it is the oxygen of carbon 1 that is attached to carbon 5. Okay, so let's continue. Now, what else happens here? Once you attach to carbon 5, the hydroxyl group in carbon 5 will move from carbon 5 and go to carbon 1. That is basically what happens. So instead of this OH to be here, we move it here to carbon 1. And then you feel the rest of the things that was there. Now let's do this together. Let's do this together. Initially on this carbon, we had just one hydrogen. So we put one hydrogen. Then, as I said, the OH in carbon 5 will move to carbon 1. And you have OH here. I'll continue. In carbon 2, you will notice something in carbon 2. There is one hydrogen and one OH. So let's do the same. We have one hydrogen and one OH. Basically that. And then we go to carbon 3. In carbon 3, we have one OH and one hydrogen. And you have that. In carbon 4, what do we have in carbon 4? We have one OH and one hydrogen. Then in carbon 5, we have one hydrogen and one OH. But I told you that the OH of carbon 5 is transferred to carbon 1. And basically, this is the cyclic version of glucose. And that is how it works. So you just notice something. Please also notice that I had, if you notice, the position of carbon 3, H was inside. If you notice, I had to change the others have OH on the outside, basically, to show that the arrangement of OH and H plus in carbon 3 is different. So you have to also indicate that difference when you are putting this structure together. Okay, so you have that. In converting the straight chain to cyclic, first of all is the anomeric carbon atom, which is the one carrying carbonyl, attaches to oxygen, and the oxygen of that anomeric attaches to carbon 5. Okay, we forgot to fill up the sixth carbon. Sixth carbon is CH2 and then OH. Basically the same thing. So you have that as this. This is the cyclic version. Please, this is carbon 1, the same numbering basically, but then I had to restructure it. If this is not understood, please indicate so that I would re-explain. If this is understood, also indicate. Okay? Please indicate. Okay, so I think I'm going to just have to continue. Now, having said this, it's important to also have this in mind. Hmm? With this arrangement, it makes it easier for us to be able to identify the alpha glucose and the beta glucose. Now, alpha glucose, if you notice the positioning of the hydroxyl in carbon 4, once the OH of carbon 1 and 4 in the cyclic version coincide, that is OH is down, OH is down, you refer to it as alpha. But in a scenario where this OH is now up, it becomes beta. Okay, let me redraw this structure again to help us understand this. I'm going to redraw the structure from scratch. I have C1, 2, 3, 4, 5, 6. Every other thing you have OH. The only place you have a difference is on carbon 3. Every other place is OH on the right side. OH on the right side. Every other thing is OH on the right side. Yeah, because I have hydrogen on the right side, OH will now be on the left on carbon 3. Basically that. Now remember I told you that what happens in the formation of cycles is 1, 2, 3, 4, 5, 6. You have that O is attached to carbon 5. And when this attachment occurs, OH will now go from here and go and attach this. So let's draw it. We start from carbon 1, which is the anomeric carbon. This is carbon 1 attached to oxygen, and this oxygen is now attached to carbon 5. Remember, carbon 5 has attachment to carbon 6 here. So carbon 5 will go to carbon 4. From carbon 4, you go to carbon 3. From carbon 3, you go to carbon 2. From carbon 2, you come back to carbon 1. Now, remember that I said that the OH in carbon 5 will have to come here. Now, if that OH is up here, hydrogen will be down, OH is here. In this case, carbon 3 has the difference, so hydrogen has to be here and OH is here. Carbon 4, OH is out, hydrogen is up. Then I come to H. Here, it's two hydrogens. I can just write H2OH. Okay, so let's look up. If you notice in this case, carbon 1 has the OH in the opposite direction to carbon 4's OH. Because of this, this is what we refer to as a beta glucose. A beta glucose, the OH in carbon 1 is opposite to the direction of the OH in carbon 4. This one is what we refer to as beta glucose. But in the case of alpha glucose, if it was an alpha glucose, okay, let me try putting in an alpha glucose here. This is going to be C O C C C C C. Okay, so yes, and then you have CH2OH. Then here you have hydrogen, you have OH, OH, hydrogen. In carbon 3, that's where the difference is. This carbon 1, 2, 3, 4, 5, and this is 6. In carbon 3, that's where the difference is. Hydrogen is out, OH is in. And here OH is out always. Okay. So if you notice, because carbon 1's OH is in the same direction as carbon 4, this particular guy will now become an alpha glucose. So just have that in mind. The difference between an alpha glucose is simply dependent on the direction of the OH. That is one thing I would like to say. Why I'm mentioning this thing is when we get to the bonds between monosaccharide units is what we refer to as your glycosidic bonds. And there are different types for your polysaccharides. Okay, before I leave, let's do that of fructose and see how it should look. If you are dealing with fructose, fructose is CH2OH, C double bond O, C hydrogen, every other thing is the same. OH, OH, hydrogen, 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 OH. Now remember, the anomeric carbon atom in fructose is not carbon 1, it's carbon 2. So it's going to join from here to carbon 5. This is 3, this is 4, this is 5, and this is 6. So let's get to do this now. So we're going to start with carbon 2. Carbon 2's oxygen will join to carbon 5. Now, but remember that carbon 2 is also carrying carbon 1, which has H2OH. And carbon 5 is carrying carbon 2OH. And with this now, we will continue to carbon 4. From carbon 4, we continue to carbon 3. And from carbon 3, we go back to carbon 2. Now, with this particular structure, now, this is the cyclic version of fructose. And the same thing applies. In carbon 2, the OH in carbon 5 will now be transferred here. So you're going to have this. Carbon 3 is where the difference is. H and OH in. Here you have OH. Here you have H. And here you have H. Now, if you look at this particular structure, because the OH and the OH are in the same direction for the anomeric carbon atom, automatically this becomes alpha. In this case, it's 2 and 4, not 1 and 4. In this case, it's 2 and 4. Because they are in the same direction, you refer to them as the alpha fructose. In the case of glucose, when 1 and 4 were in the same direction for the OH group, we refer to it as the alpha glucose. Okay, I don't think I should overemphasize that. Let's move ahead. Now, the most important oligosaccharides that we need to consider are your disaccharides. Disaccharides. And disaccharides are formed by combining two monosaccharides. Two monosaccharides. The process of combination is what we call condensation reaction. In condensation reaction, it involves removal of one molecule of water. So have that in mind, that in this form of reaction, you are removing one molecule of water. We are going to consider important. I'll give you a general equation. The general equation for formation of disaccharide is C6H12O6 plus C6H12O6. When it reacts, let's remove one molecule of water first. You remove water. Now, if you remove water, you just combine the rest of them. So you have C6 plus C6 is C12. H12 plus H12 is H24. Now, but remember that we removed 2. So 24 minus 2, what is going to be remaining is 22. O6 plus O6 is 12. But remember that we removed 1 to get water, and what is going to remain is 11. So this is the general formula for your disaccharides. This is general formula. Now, the important thing you need to note is that glucose plus glucose combines to form maltose and water. Glucose plus fructose combines to form sucrose and water. Glucose plus galactose combines to form lactose and water. Maltose is the sugar you find in malt. That's all your barley them. Sucrose is the one you find in sugarcane. In fact, it is actually the normal sugar we use to drink tea. The cube sugar is sucrose. Lactose is your milk sugar. You will notice that anytime you hear the term lact, it simply deals with milk. Now, I would like to say something about carbohydrates. Carbohydrates, when you're talking about carbohydrates, eh, as we said, they are classified into the monosaccharides, the disaccharides, the oligosaccharides, and the polysaccharides. Then, however, you can classify it based on sweetness. Please, the only class of carbohydrates that are referred to as sugar are the ones that are sweet. The ones that are not sweet are not called sugar. For instance, will you say that starch is sugar? No. You can go and eat raw yam and see if it is sweet. Raw yam is not sweet now unless you boil it. So just have that in mind that when you are dealing with unsweet carbohydrates, they are not referred to as sugar. The only sweet carbohydrates we have are your monosaccharides, and your disaccharides. Your monosaccharides and your disaccharides and your disaccharides. So these are the only two class of carbohydrates we refer to as sugar. Why are they called sugar? Because they are sweet. The other ones are not sweet, so they are not referred to as sugar. So just have that in mind. Okay, now I would like to show you just one simple thing about this. Eh? Maltose, if it is broken down, it will give glucose plus glucose. The enzyme that will break down maltose, just replace this O with A, and you have that the enzyme that will break down maltose to get glucose is maltase. Sucrose will become sucrase. Lactose will become lactase. Quite simple. So just in case you come across a question and you are asked, what is the enzyme that digests maltose? You simply remove the O and put A. It becomes maltase. Sucrose, remove O and put A. It becomes sucrase. Lactose, remove the O and put A. It becomes lactase. Basically. So just have that in mind. Okay. With that said, I just want to check, are we still following? Abi we have go and sleep. I know you have exam tomorrow, so in the next 30 minutes, I'm going to have to stop so that you guys will go and read up for your exam. Okay. Chukwu Stanley, can you please indicate exactly where you need explanation so that I will come back to that, please? You get. Okay. Now, having said that, while pending your reaction, let's just move ahead. Having said that, let's look at this. Let's look at this. So just have that in mind that if you, the reaction that is used to produce your disaccharide is a condensation reaction, you get basically. And the type of bond that is formed between monosaccharide units, bond between monosaccharide units is what we call glycosidic bond. The one that is formed between your your amino acid is peptide bonds. I take it again. The type of bond that is found between monosaccharide units in carbohydrates is glycosidic bond. In the case of amino acid, it is peptide bond. So please take note of these two major bonds. Why I'm saying it is amongst your classes of food, the only polymers amongst your classes of food, major polymers among the major classes of food, that's protein, carbohydrate, and fats and oil. The polymer amongst them is the polysaccharide carbohydrates and your protein. Your fats and oil are not polymer. Fats and oil are simply esters. We are likely to touch one or two things about that. Now let's move ahead. Now, with that said, I have mentioned that glycosidic bond is characteristic to carbohydrate, while peptide bonds is characteristic to amino acid. Okay, so I have touched the disaccharide, and I would like to move ahead into the polysaccharide. Things to note about the polysaccharide. The polysaccharides are formed by polymerization. The exact type of polymerization is condensation polymerization. I told you that in condensation polymerization, it involves removal of one molecule of water or any other thing. But with respect to carbohydrates, when you are doing condensation polymerization, you are removing one molecule of water. Now, with this said, you would have to join different monosaccharides in regular patterns to get your polysaccharide. And the general molecular formula of polysaccharide, the general molecular formula of polysaccharides is C6H10O5 bracket N, where N is representing a large number. But the point is, every polysaccharide has this particular guy as the general molecular formula. Now, we are going to be considering major polysaccharides. The major polysaccharides we are going to consider are starch, cellulose, glycogen, and then insulin. Now, in these three, glucose is the monosaccharide unit or the monomer. Glucose is the monomer. Glycogen, glucose. But when you come to insulin, fructose is the monomer. So the monosaccharide that forms starch, cellulose, and glycogen is glucose. But the one that forms insulin is fructose. These are just major points I want you to take note of. The monosaccharide that forms starch, cellulose, and glycogen is glucose. But the one that forms insulin is fructose. Point number one. Now, the second thing about starch, cellulose, glycogen, insulin, all of them are polysaccharides and they are not sweet. They are not sugar. I tell you that the only ones we refer to as sugar are your disaccharides and your monosaccharides. So, talking about starch now. Number one is that starch is made up of the two major polymers that are found in starch are the amylose and amylopectin. I'm going to say something about these two guys. I take it again, amylose and amylopectin. In amylose, this is for starch. These are where some of your technical questions might come from, so please listen. When you are dealing with amylose, amylose, the type of bond that you find in amylose or linkage is what we refer to as unbranched alpha 1,4 glycosidic link or bond. Amylose has 1,4. 1,4. I will come back to this, but just know it now for want of time. Amylose has alpha 1,4 unbranched, but amylopectin has both alpha 1,4 and alpha 1,6. Amylopectin has alpha 1,4 and alpha 1,6, but amylose has only alpha 1,4. These are the two polymers that you find in starch. I take it again. In starch, the two major polymers that are found in starch are the amylose and the amylopectin. What is the difference? Amylose only contains unbranched alpha 1,4 glycosidic link. But in the amylopectin, you have alpha 1,4 and alpha 1,6. Usually, the alpha 1,6 is branched. So just have that in mind. Alpha 1,6 is branched, alpha 1,4 is unbranched. So just have that in mind. Now, the next, cellulose. I presume this is understood. If you do not understand so far, okay. It's a live class, so you guys are permitted to comment. I hope this is clear so far. Okay. Is it clear? If it's not clear, you can just indicate. indicate? Okay, so just have that in mind anyway. That when you are considering your starch, when you're considering starch, starch has two major polymers, the amylose and the amylopectin. Amylose and the amylopectin. Okay, just give me a little moment to resolve something. Okay, so now having said this, I presume you are still with me. Let's just continue. Having said this, um, the next one that I think I need to highlight is the cellulose. What is now the difference between starch and cellulose? Now, the major difference between starch and cellulose is dependent on the glycosidic bond. Now, in starch, you will find alpha 1,4 glycosidic in starch. I said starch has two, amylose and amylopectin. Here you only have alpha 1,4, but here you have alpha 1,4 and alpha 1,6. In the case of glycogen, cellulose. In the case of cellulose, the difference between starch and cellulose is that number one is that it doesn't have two polymers, and then the type of glycosidic bond in cellulose is beta 1,4 glycosidic linkage. So just have that in mind. Starch, cellulose, and glycogen. Starch, cellulose, and glycogen are all referred to, or their major base is glucose. It is glucose that forms these three polysaccharides. But the difference is number one is that starch is classified into two, it has two polymers, the amylose and the amylopectin. The type of glycosidic bond, I told you that anytime you are looking at the bond between monomer units or monosaccharide units in carbohydrate is glycosidic. The type of glycosidic bond in starch is 1,4, amylopectin is 1,4 and 1,6. But in the case of cellulose, it is beta 1,4, not alpha. Then finally, glycogen. Glycogen is likened to the amylopectin, exactly likened to the amylopectin, which means glycogen has alpha 1,4 and it also has alpha 1,6. Remember, I told you this one is on branch, while this one is branch. We're going to discuss these things more in details in your second semester. I'm just trying to highlight what you need to know. Now, the difference between glycogen and this one is that this one has more branching than this one. So just have that in mind. That when you think about cellulose, it is cellulose that has the beta 1,4 glycosidic linkage, basically. With that said, I would like to round it off at that point. Now, starch is the storage. That's how carbohydrate is stored in plants. Cellulose is found in the cell walls of plants. And then finally, glycogen is carbohydrate stored in animals. I'm just highlighting these important things so that we can be able to notice these things. Okay, I came across a question. So let me just highlight it basically. I think I came across a question that has to do with this. Uh, okay, let's answer these questions basically. We might not talk about question 19 now, but let's start with question Okay, but let me just say, linoleic acid is an example of dash fatty acid. The answer is unsaturated fatty acid. Why? Linoleic acid is basically how do I put it? Yes, linoleic acid is octadec 912 enoic acid. The point is that it has double bond. And I told you yesterday that once you see double bond, it is unsaturated. So that is why the answer is unsaturated. Linoleic acid is an unsaturated fatty acid. Let's leave that. We will still discuss it probably. Number 20, fat and oil undergo hydrolysis in the presence of enzyme lipase. Fat and oil digesting enzyme is lipase. Protein digesting enzyme is protease. And then carbohydrate digesting enzyme is amylase. Okay. In D and L configuration of monosaccharides, when the position of O is on the right hand side, yes, I did not mention this. Now, we are supposed to understand enantiomerism. I have a video on that. You can go and look that up if you want to understand it. But I'm just going to say one thing. When you talk about optical isomerism, it means that the plane of a polarized light is turned towards the right or towards the left. Hmm? If it is turned towards the right, you call it dextroenantiomerism. That is D. That's what D means there. D is dextro. When it is turned towards the left, it is level. So think left, level, right, dextro. In carbohydrates, the OH positioning of number 5 is what determines all these things. If the OH group on number 5 carbon is on the right side, it means it will turn the plane of the polarized light towards the right. And I told you, right is dextro, left is level. So please, the implication is that you're going to have a D sugar. So just have that in mind that the answer is going to be E. You are supposed to have a D sugar. Why? Because it is turning the plane towards the right. Once it turns the plane towards the right, is dextro. Towards the left, is level. And I told you that what determines this thing in glucose is OH. So let's move ahead from that. Maltose gives glucose plus glucose. The enzyme in the reaction is maltase. I told you guys that remove O, put A, you get it. And that's that basically. Glucose plus fructose gives dash. Yes, let's answer that. 23 is something we can answer. Yes, 23. Are we still in this class? Have we gone to sleep? Well, we don't try, Sha. After this question, I think we'll have to stop here for today. Um, Basically, we have tried. Yes, 20. Chukwuebuka Stanley, are you answering for number 23? Okay, yes. 23 is B. Chukwuebuka Stanley, you are correct. Okay, so we move to number. Just put your number when you want to give an option from 23 to 24. I presume you guys can answer it too. Put number 23, answer, 24, answer, 25, answer quickly so that we can move ahead. Option 25 has some typographical error. Those places you have amylor. What is supposed to be there is amylose, not amylor. You get, so every place you see ORE is OSE. That should be there in number 25. So what's the answer to number 24? 24 B. Okay, let me explain. Did you remember that we said starch is the form in which carbohydrates are stored in plants, which means that starch is a storage polysaccharide. Cellulose is not stored in plants. Cellulose is the part of the structure of the cell wall, which implies that cellulose is a structural polysaccharide. Cellulose is a structural polysaccharide. And then this other guy, glycogen, is also a storage because it is the form in which carbohydrate is stored in animals. I mentioned that when I was differentiating between the three of them. Starch is a storage polysaccharide. I hope this is clear, which means glycogen is also a storage polysaccharide, while cellulose is a structural polysaccharide. Insulin is not a storage because that's not how it is stored. It is also under structural polysaccharide. Are you getting what I'm saying? So just have that in mind. That when you are looking at the forms in which it is stored, you are looking at storage polysaccharide. But the forms in which the parts that make up like structures or parts of a particular body is referred to as the structural. Talking about this, if you come to the lipids, the storage lipids that you have are just your fats and oil and waxes. And when I say fats and oil are generally also known as triglycerides. I'm just saying these things just to highlight one or two points. Okay, then we go to number 25. The two types of starch. When they say two types of starch, they are telling you the two things that are inside starch. And the answer is amylose and amylopectin. Yes, that's the answer. The answer is C. Okay, so with that said, I think we can move ahead. Um, we don't try, eh? What I'm going to do is this. Most of you have my number. If you don't have my number, anybody that you saw the link on the status has my number. I'm going to be joining you guys to study. If you have questions, chat me up directly on any of the concepts you read that you are confused in, and I would have to respond. I would like to give you guys your own time to go and study. So go back, study, and chat me up directly on questions you are confused about. I wish you guys good luck in your exam. We are not able to cover everything. There are still lipids. You get. And what I would like to say about lipids is this. Um, Let me just highlight one or two things before we end the class for today. For lipids, let me highlight one or two things. Just put it out there. Maybe it might come out, maybe it might not. Let me just highlight one or two things before I leave lipids. Before I leave end the class. Now, when you hear lipids are characterized by insolubility in polar solvents. That is to say, they are highly insoluble in polar solvents. Now, generally speaking, based on their solubility, lipids can be classified into two. The first class of lipids are referred to as your hydrophobic lipids. If I say hydrophobic, you are seeing phobia. Phobia means fear, which implies that they are afraid of water. Hydro is water, phobic is fear, which means they cannot dissolve in water. So have that in mind. The hydrophobic lipids are the lipids that are insoluble in water. Now, these hydrophobic lipids constitute the part of lipids that are referred to as storage lipids. And the two storage lipids you have are your triglycerides. When I say triglycerides, it is fats and oil. And the second storage lipid you have is wax. Now, when you will notice wax, you will notice that your sebaceous gland, for those of you that have read through the other parts of your Bio 151, your sebaceous gland is a part of the skin that produces waxes that lubricates the hair. If you did your biology properly in secondary school, you should understand what I'm saying now. So that wax that is produced by the sebaceous gland that oils the hair and keeps your skin oily is is a wax, or the oil is not oil, is not fat, it is under wax. And both of them, both triglyceride, fat and oil, and waxes are referred to as storage lipids, and they are all hydrophobic. The other class of lipids are referred to as amphipathic. When you hear amphi usually means this side or the other side. So that is to say, amphipathic, they have both polar and non-polar ends. That is one thing about amphipathic. They have both polar and non-polar ends. The hydrophobic only have non-polar. If you notice, non-polar compounds should be insoluble in water. Hydrophobic only have non-polar, but amphipathic have both polar ends and non-polar ends. That is what differentiates them from these guys. Now, all amphipathic lipids are structural lipids. We did this thing in carbohydrate. I mentioned that starch is not structural, starch is storage, meaning that it is stored in the body. So fats and oil is stored in the body, waxes are stored. But these structural lipids are not necessarily stored. They are usually parts of structures inside the body. Okay, now the major classes of the structural lipids, I'll just highlight them.